Let's imagine that you have a very heavy truck and a small car moving side by side in a highway, so at exactly the same speed. Which one will have the highest quantity of motion? I'm using the expression quantity of motion on purpose because I think that using this expression will give you a more visceral idea of the topic of this chapter, which is momentum. So the question could be the same if I would use the word momentum instead of quantity of motion. So the question again, car, truck, moving side by side at the same speed in a highway. Which one has the highest momentum or quantity of motion? If you think of it a little bit, I think that it's going to be obvious that a truck, because it's much more massive than the car, will have a much higher quantity of motion. The visceral understanding will be deepened if you think of these two vehicles stopping. Which one is easier to stop? The car. Not because it's moving at a high speed, it's not, it's moving at the same speed as a truck, but because it's much lighter, it's much easier to stop. The quantity of motion that the truck carries with it makes it much harder to stop. It carries a much higher inertia. All right? Now let's think of another situation. You have a huge cruise ship stopped at the harbor, and by its side you have a bumblebee going from flower to flower. Which one will have a higher momentum? In this case, the mass of the cruise ship, which is, I don't know how many times bigger than the bumblebee, will have no impact whatsoever because the speed of the cruise ship is 0. And no matter how light the bumblebee is, just because it is moving, it will have a higher quantity of motion, a higher momentum. So what are the two factors that influence momentum? It's the mass and the velocity. Momentum is given by this lowercase p, and a very important thing that I want you to retain, and I cannot express how important this is the fact that momentum is a vector, and this is not speed, this is a velocity. So the direction matters. If you treat this as speed, then chances are, or most likely, all your answers to the questions are going to be wrong. Okay, and I'll explain the reason in a bit. What are the International System units for momentum? This is in kilograms, this is in meters per second, so it's kilograms meters per second, or newtons second. The reason for Newton second is going to be obvious also. Actually, no, this is more in physics. You can use both, but in the context of mechanics, you might as well just use kilograms meters per second. As a vector, momentum's direction may be defined by its sign, positive or negative. You define previously what positive is, or the question will define that for you, and you stick to that until the end of the question. If, for example, it says that to your right it's positive, then every vector that points in that direction is going to be positive. Any vector that points in the opposite direction is going to be negative. One important thing that you need to know about momentum is that if you have a system, in mechanics you are going to have just two objects in this system. And if you may imagine the whole universe just made out of these two objects. If you would add the momentum of object 1 and the momentum of object 2, and nothing else happens in the universe is made out of those two things, the total momentum is going to be kept the same until the end of time. It doesn't matter if the objects are ever going to interact with each other or if they will. Even if they collide, the total momentum after the collision is going to be kept the same. Similarly, if you have a single object and the universe is made out of only this object, if this object has a certain momentum, it's going to have this momentum until the end of time. And even if this object suddenly explodes and divides in two, the momentum of this section and the momentum of this section added together is going to be equal to the momentum that the object had before. Why do I say this idea that the universe is made out of just these things? For you to perceive that the system is isolated. The idea of isolated system is a system in which the objects that compose the system do not interact in any way or fashion to the anything that goes outside of the system. Okay, so thinking of the universe as being made out of just these things helps you visualize this idea. Okay, so in an isolated system, the net momentum, the momentum of all its components added together, is always the same. It is conserved. This is the law of conservation of momentum, one of the most important laws in physics. And this has implications on collisions and explosions, as I mentioned. Let's go a little bit deeper talking about collisions. So let's imagine that you have two particles that are about to collide. And if that's the case, they may be considered an isolated system. Again, think of these two particles as the only thing that exists. There are no interactions between these particles and anything else. All right? This means that the total momentum before the collision is going to be equal to the total momentum after the collision. Mathematically speaking, you can represent it like this: PTI, so this is the total momentum, I for initial, equals PTF, the total momentum, F for final, the total momentum after the collision. You have only two objects, so what is this? This is going to be the mass of object 1 times the initial velocity of object 1. That's what U stands for. So m1u1 plus the mass of object 2 times the initial velocity of object 2. This is the momentum of object 1. This is the momentum of object 2. Added together is a total momentum before the collision. Is the same, equals to the mass of object 1 times the velocity of object 1 after the collision, plus the mass of object 2 times the velocity of object 2 after the collision. A good way for you to visualize this is thinking about a game of snooker with two balls. Now, let's forget the interactions between the balls and the surface of the snooker table or the sides of the snooker table. Let's just focus on the two balls colliding, okay? The total momentum before the collision of the two balls is going to be the same as the total momentum after the collision, after they collide, and each one goes in a different direction. That's why it is important to think about velocity and not speed, because here the direction is going to matter. All right? You, in mechanics, in a context of mechanics, don't need to worry about collisions in two dimensions. Everything is just going to be on a single dimension, okay? So you may have situations in which you have something going that way, and this one has a higher velocity, hits, and they are going to change their velocities, all right? Or one thing going against the other, all right? But in both cases, it's just in one dimension. If you understand that these are vectors and the signs will matter, okay? Don't forget, in one dimension, you define what positive is. So you need to think of each one of these. And if they go in the direction that you decide is positive, in which case these are going to have positive values. Or if they are moving in the opposite direction, in which case these are going to have negative values. If you never forget that and you apply this, then this equation is going to be used in all situations. All right? What about explosions? An object exploding in two pieces may also be considered an isolated system. Again, if an object is going to explode in the context of mechanics, AS level, this is just going to happen in two situations, in one dimension, sorry. So, what else I was thinking of? Give me a second. Yes, and this object is going to be also considered an isolated system. Now I want to pay attention to the idea of what an explosion is. An explosion is any situation in which an object, the initial circumstance of an object, is going to be, for some reason, separated into two. Okay? I simplify to call explosions because it's simpler to visualize, but this could be, for example, me moving on a skateboard. Okay? So I have the single object in the beginning as me plus the skateboard as a single object. And then I jump to the back. Okay, so the skateboard goes in that direction and I go to the back, and this initial system, me plus skateboard, is divided into two. Okay, so that's what I mean with explosions. So here the total momentum is also going to be conserved. What is a total momentum before? It's just the mass of the single object, okay, so mt for total mass, times the velocity of the object before the explosion is going to be equal to, and now we're going to have two pieces, the mass of the first piece times the velocity of the first piece after the explosion, plus the mass of the second piece times the velocity of the second piece after the explosion. Is just the same idea, but now applied to the circumstances that are being described.